Imagine shining a beam of light through a completely transparent material. Most of the light passes straight through, but a tiny fraction of that light does something unexpected. It comes out with a slightly different energy. The light has changed, not because the material absorbed it completely, but because the light interacted with the molecules themselves. This phenomenon is called Raman scattering. But what exactly is happening? Light can be thought of as packets of energy called photons. When a photon enters a material, it interacts with the electric charges inside its atoms and molecules. Most of the time, the photon is scattered without changing its energy. This is called Rayleigh scattering. The scattered photon has essentially the same frequency and therefore the same energy as the photon that entered, but something much rarer can happen. The photon can exchange energy with the molecule, and that's where Raman scattering begins. Molecules aren't perfectly still. Their atoms are constantly moving. They can stretch, bend, rotate, and vibrate in different ways. These molecular motions have specific, quantized energy levels. When light interacts with a molecule, it can exchange energy with one of these vibrational modes. The photon may leave with slightly less energy or slightly more. Here's the strange part. The photon doesn't simply collide with the molecule like two billiard balls. Instead, the interaction involves a temporary quantum state called a virtual state. The incoming photon briefly disturbs the molecule. Then the molecule returns to one of its allowed energy states. If the molecule gains energy, the outgoing photon loses energy. This is called Stokes-Raman scattering. The incoming photon has a certain frequency. After interacting with the molecule, the outgoing photon has a slightly lower frequency. Because photon energy is related to frequency, E equals hf, a lower frequency means lower energy. The missing energy has gone into the molecule's vibration. The scattered light, therefore, carries a fingerprint of the molecule's internal motion. But there is another possibility. The molecule can already be vibrating in an excited state. During the interaction, it can give some of that vibrational energy to the photon. The photon leaves with more energy than it had before. This is called anti-Stokes-Raman scattering. So Raman scattering can work in both directions. Light can give energy to a molecule or take energy from it. Now imagine measuring the scattered light. Most of it is still Rayleigh scattering. A huge central peak remains at the original frequency. But hidden beside it are tiny additional peaks. These are the Raman lines. Their positions reveal the energy differences between molecular states. And because different molecules have different vibrational energies, each substance produces its own characteristic pattern, a molecular fingerprint. Think of it like a barcode made of light. A particular molecule has particular bonds. Those bonds vibrate at particular frequencies. So when a laser interacts with the molecule, the resulting Raman spectrum reveals information about those vibrations. Scientists can use this information to identify substances without destroying them. The phenomenon was discovered in 1928 by Indian physicist Sir Chandrasekhara Venkata Raman working with K.S. Krishnan. Raman found that when light passed through certain materials, a small fraction of the scattered light had frequencies different from the original light. This was remarkable. The light itself was carrying information about the microscopic structure of matter. In 1930, Raman was awarded the Nobel Prize in Physics for this discovery. Today, Raman spectroscopy turns this phenomenon into a powerful scientific tool. A laser is directed onto a sample. The scattered light is collected. A spectrometer separates the different frequencies, and a computer produces the Raman spectrum. From that spectrum, scientists can determine what the material is made of. Raman spectroscopy has applications across science and technology. It can help identify pharmaceutical compounds, analyze minerals and crystals, study chemical reactions, examine pigments in works of art, and investigate materials such as graphene, semiconductors, and other advanced materials. Because the measurement can often be performed without destroying the sample, Raman spectroscopy can be incredibly useful. And Raman spectroscopy can go even further. With Raman microscopy, scientists can focus the laser onto extremely small regions. Instead of simply asking, "What is this material?" they can ask, "Where is each chemical component located?" A Raman microscope can create detailed chemical maps of microscopic structures. Light becomes a tool for seeing chemistry. But Raman scattering reveals something deeper. It connects the world we see with the quantum world we cannot see directly. A molecule may be far too small to observe with our eyes. Its vibrations happen on microscopic scales. Yet those vibrations can leave their signature on a beam of light. The information is encoded in a tiny shift in frequency. And that's the key idea. Raman scattering isn't simply light bouncing off matter. It is an exchange of energy between light and molecular vibrations. The incoming photon interacts with the molecule. The molecule briefly enters a virtual state, and when the system returns to a real molecular state, the photon can emerge with a different energy. That tiny change is the Raman effect. And here's the remarkable part. Those tiny shifts can tell us enormous amounts about matter. They can reveal molecular bonds, chemical composition, crystal structure, stress and strain, and even changes occurring inside complex materials, all from analyzing light. So, what is Raman scattering? It is the rare scattering of light in which photons exchange energy with matter, leaving behind tiny shifts in their frequency. Those shifts are not noise. They are information, a molecular fingerprint written into light. And that is what makes Raman scattering so extraordinary. A beam of light enters a material and comes back carrying a message about the molecules it encountered. Sometimes, to understand matter, you don't need to see the molecules. You just need to listen to the light.